In this particular section, we've been talking about two applications of integration. In the last video, we talked about how to find the length of an arc or the length of a curve from some x value to some other x value, or from some y value to some other y value. In this part of that section, we're going to be taking a look at surface area of a shape that has been revolved. So we've done this before, but we are looking at the volume of this surface that got revolved. And now we want to talk about the surface area of that shape that got revolved. So instead of how much can we pack inside of it, how much paint would it take to paint the outside of it? So when we're looking at this, we can think of it as either the bare minimum amount of paint needed to barely cover the surface exactly one time, or we can think of it as the amount of wrapping paper needed to wrap the solid without any gaps or overlaps. So we want to know, how do we compute the surface area of some shape that looks like this? So you can see here that we have a curve, y equal f of x in orange, and it's been revolved around the x-axis, producing this solid of revolution. So in the past, what we were looking at was what was the volume of this solid of revolution. Now we want to know, well, if I want to paint it, how much paint do I need? So we're looking at the surface area of this volume of revolution. Now we're going to do pretty much what we always do, which is we're going to partition the interval from A to B, wherever we revolved it. And we're going to approximate the surface area by calculating the surface area of some simpler shape. Now, the particular shape we need is something that you may not be familiar with. It's called a frustum. It's shaped like a yogurt cup. So if you think about a yogurt cup, it's flat but circular on the bottom, and it's circular on the top, and they're parallel to each other. But the top is a smaller radius than the one on the bottom, and they're concentric. They have the same center. So when you're thinking about a frustum, that's sort of the shape you want to think about. Or if you've seen on TV or somewhere in a circus, when an elephant stands on one of those little platform things, that little platform is a frustum. It has a circular base, which is flat, and a circular platform on top. But the platform on top has a smaller radius than the one on the bottom, and they're concentric. It's got flat sides as well. So let's go ahead and see how we can form a frustum, where it comes from. It basically comes from a right circular cone. So that's a cone that's, where the axis is perpendicular to the base. And we just chop off the top. And if we chop off the top parallel to the base, then we end up with a frustum of a right cone, which looks like this right here. So if we're looking at that in terms of our graph, you can see that what we've got is a smaller radius R2 on the top surface and a longer radius R1 in the bottom surface. And the edges of this thing are completely flat. They're not curved, but it's slanted. So we call that L, the length of the slanted curve. And this is sort of what it looks like represented in a more 3D format when you're looking at a frustum. So how can we use this frustum? How does this come into play when we're doing a volume, or rather a surface of revolution of some solid? Well, what we want to do is we want to take that frustum and we want to cut it along the vertical. So when we're looking at this frustum here, we might make a cut right here along this vertical line. And then we kind of peel it open and flatten it out. Now, when you flatten it out, because the top was a circle and the bottom is a circle, these aren't going to be line segments. They're going to be arcs. All right, so we're looking at this right here. And of course, this right here is the circumference of the circle for the top, and this blue on the bottom is the circumference for the circle on the bottom. And the red lines on either end are the slanted links along the edge of the frustum, this area right here. So now what we want to look at is we want to think about how we can take this shape that we've got and how does it apply to the function that's been revolved around an axis, creating some solid of revolution. Well, in order to do that, we want to first go ahead and label R2 and R1 in this flattened out section. If we flatten it out, you can see that R2 goes from the center to the edge, and R1 does as well. And R1, of course, is going to be longer than R2 because it's coming from the base, which has a larger radius. If we take this image and we rotate it 90 degrees counterclockwise, we end up with this image right here. So again, you can see R2, which is right here, which is the radius of the upper one. And then you can see R1, which is right here, which is the radius of the base. And then that slanted length L actually becomes sort of the top, right? So when we're looking at that, that's what we end up with. Now, if we're looking at this particular picture here, this is going to be a part of a shape of that solid of revolution. So we revolved it around, and I'm going to show you what it looks like. But this is going to come out in that solid of revolution. Now, R2 is going to become f of x sub k minus 1, and R1 is going to be f of x sub k. So R2 is to the left, and R1 is to the right on our particular picture. So how does that happen? Well, let me go ahead and try to draw one for you right here. So here's the frustum. And curved, and it of course comes around in the back as well. And I'm not very good at drawing these, so you're really going to have to use your imagination because Lord knows I can't draw. All right, so when we're looking at this right here, you can see that this edge right here is sort of that curved piece. And actually, this represents the frustum not flattened out because it goes all the way around. It is, in fact, the frustum itself. But this distance here is our R1. So this value right here, and of course I've tried to draw it sort of like 3D. This is going to correspond to our R2, which is this right here from the center up, from where it was revolved up. So this is R2, which is f of x sub k minus 1. And this one right here is going to be R1, which is f of x sub k. Right? And again, that's measuring the distance from the axis of revolution up, right? So it's, of course, the radius of the circle created by the frustum on the top and on the bottom. So this is where the frustum comes into the shape. Now, notice that what we have on this edge is not really flat like the frustum is. So the frustum, of course, is completely flat along that edge. But ours is not really a true frustum because this edge isn't totally flat, although it looks more or less flat. It's actually part of a curve, and that curve is the function, which also gives us the radius values. So we need to figure out how we can approximate all the surface area of the frustum in order to approximate the surface area. Now, you know what we're going to do. We're going to take n different frustums coming all the way across. We're going to find the surface area of each one, add them together, and take the limit as the number of frustums goes to infinity. Now, in geometry, it can be proved that the formula for the surface area of a frustum, that round yogurt cup shape, can be given by pi times the sum of the two radii, the upper circle and the lower circle, times that slanted length, L. So that's pi times the sum of the radii times the slanted length L. That gives the surface area of one frustum, all right? So if you want to take your yogurt cup and you want to paint it, that's what you need in order to paint it. So now what we're going to do is we're going to take this formula and we're going to try to create something that will approximate the surface area of this solid of revolution using this formula right here. So the next step that we're going to take is we're going to use arc length to approximate that slanted L, that slanted side length L. So instead of using L, we're going to use the arc length formula, which you see right here. So this part right here replaces L, which is that slanted flat edge. But ours isn't really flat. Ours actually is arc length. So this is slanted flat edge on a frustum. And we're going to approximate that using the arc length. And the arc length, as we saw in the last video, is the square root of 1 plus the derivative at some value, quantity squared times delta x or dx. Now, our formula, of course, is pi, sum of the two radii, times L, which we're approximating with the arc length formula. So this is still the formula for the surface area of a single frustum. And this is L-ish. All right. So now what we're going to do is we're going to look at this and see if we can simplify this formula, because after we sum them together, we're going to take the limit as n goes to infinity. We want to be able to integrate. So when we're looking at this right here, we can apply the intermediate value theorem. Because we're using the arc length formula, we have to require that the curve be smooth. So again, that means it's continuous, it has a first derivative, and the first derivative is also continuous, which is a pretty strong condition. So when we're looking at this, we can then apply the intermediate value theorem because it only requires continuity. And we remember that the intermediate value theorem says if it's continuous and it hits two values somewhere in between, it has to hit every value between those two numbers. So for example, if you have a curve that looks like this, and you know that this is on the curve and this is on the curve, then every y value between here and here has to be represented somewhere between A and B, right? So again, this is our A and this is our B. So if I want this value right here, there has to be some special spot right there, which we're going to call x sub k double star, since I've already got a star for the arc length. Then we've got an x sub k double star. There has to be a place like that because it's continuous. You can't get from here to here with a continuous curve without hitting every y value in between. And we're going to take that point right there, and we know that somewhere this point has to represent the average of R1 plus R2. So because it's continuous, R1 plus R2 divided by 2 is the point halfway in between those two y values. It's a continuous curve, so you know it's got to be on there. And this will give us f of x sub k double star equal to half of the radius on the left and the radius on the right, f of x sub k minus 1 and f of x sub k. That means that we can solve for the sum of the radii by multiplying both sides by 2. And that tells us that the sum of the two radii, the R1 plus R2, which actually this is in reverse order. This is R2, this is R1. This would give us 2 times the function evaluated at that special spot guaranteed by the intermediate value theorem. So now we can replace this expression right here with 2 times f of x sub k double star. So the next thing that we're going to do is we're going to take the formula, which we have right up here. So let me get my cursor working better. So here's pi, here's the sum of our two radii, and here's the arc length formula, which is approximating that flat edge L. And then we replace the sum of the two radii with 2 times f of x sub k double star. Now we've got an x sub k double star and an x sub k star. The x sub k star, remember, came from the mean value theorem, and then x sub k double star came from the intermediate value theorem. So 2 possibly different points, almost certainly 2 different points. Now what we want to do is take the limit. Now because it's a smooth curve, it can be proved that as those intervals get narrower and narrower, the value of x sub k star and the value of x sub k double star both approach the left endpoint, or x. So they both become x. So we end up with 2 pi f of x times the square root of 1 plus f prime of x quantity squared integrated with respect to x. So this gives us the formula for the surface area of that solid of revolution, not including the end caps, of course. So we're just talking about the surface itself, not the ends of it. So when we get this, here is our actual theorem. So we can do this with respect to x. We can also do it with respect to y. We want the function to be non-negative because we're going to revolve around the axis. It's just better if it's not. It can actually be done even if it does revolve that way. It's okay. Even if it's not negative, or even if part of it is negative, it still works. Then the surface area of the surface of revolution, that solid of revolution, formed by revolving the graph around the x-axis is given by this, where we have 2 pi y, 1 plus f prime of x quantity squared dx. And the second one, if we let x equal to g of y be a smooth curve over the interval from y equals c to y equals d, then we get the surface area as the integral of 2 pi x times the square root of 1 plus g prime of y quantity squared dy. Again, integrated from y equals c to y equals d. So we can do it with respect to x, or we can do it with respect to y. So it depends on which way the formula is easier or more easily applied, depending on the function that we have. And we'll look at an example of that. Now, how do I actually remember these formulas? Well, this 2 pi y or 2 pi x, depending on which way you're integrating, if you think about what 2 pi y is, we know this is arc length. So what is 2 pi y? Well, let's take a look again at that graph that we had up here where we drew the frustum. The y value, of course, is just from here to here, right? That's the y. Well, but that's the radius. So basically what we have is 2 pi r. In other words, the y value that gets into that equation is in fact the radius of that particular point. So it becomes 2 pi r times arc length. In other words, we can think of this, so this becomes r right here. We can think of it now as the circumference multiplied by the arc length formula. So circumference 2 pi r or 2 pi x if you're integrating with respect to y, and 2 pi y if you're integrating with respect to x, times the arc length formula. So we had to do arc length before we were ready to be able to do surface area. Arc length is a part of the formula for surface area. We're using this to approximate that flat edge of the frustum. All right, and we saw that this comes out of that original pi times the sum of the two radii. We were able to get this here when we took the limit. Now let's take a look at what this graph looks like over here on CalcPlot 3D. So if you have the link, if you have my lecture notes, you can go to this one. This is what this one looks like. This is the square root of x, and you can see the function over here in the 2D trace plane. And we're going from x equal 1 to x equal 4. So from 1 to 4, and then we're going to revolve this shape around the x-axis. And this is what it looks like once it's revolved. So what we're trying to find, of course, is the amount of paint it would take to cover that, the sides of it with paint. Now, we're not covering that end and we're not covering that end, but those ends would be relatively easy to find because they're circles. And then you could just do pi r squared. So you could get the entire surface area of the whole shape. So now what we want to do is we want to apply the formula. So let's work through this one together. I'm going to share my screen with you so you can see more easily what I'm writing. And we'll take a look at what we've got. So let's go ahead and take our curve, which is y equal the square root of x, and plug it into this formula. The y value itself is the square root of x. So I will replace the y variable here in the formula with the square root of x. Now I also need to find the derivative and then square it and then add 1 for the arc length part. So let's start with the arc length part. So I've copied down the information that we'll need down here. So the first thing we're going to do is we're going to find, oops, erasing as I'm writing is not very helpful. We're going to find f prime. And so the derivative of the square root is 1 over 2 the square root. And then the second thing we need to do is we need to find that squared. So when we square that, we get 1 over 4x. And then, of course, we want to add 1 to that. So we have 1 over 4x plus 1. Now, we could get a common denominator if we want to. That would be something that we could do. You might want to do that here, or you might choose not to. It'll work either way. It's just a matter of which algebra you want to employ later on in the integration. Okay, now that gives us the part that we need for the arc length. And I said that we were going to replace the y with the function square root of x. So let's go ahead and plug it into our integral. So the surface area, which I usually use SA for surface area, is going to be the integral from 1 to 4. And then we're going to have 2 pi times the radius. The radius is the function value itself, so square root of x, times the square root of 1 over 4x plus 1, integrated with respect to x. And I'm doing it with respect to x because I revolved around the x-axis. If I revolved around the y, then I would use the formula for revolving around y and integrate with respect to dy. Now, for this formula, we have to decide what algebraic steps we want to take. There are several different ways to go. They're all good. One thing you can do, since these are multiplied together and they're both square roots, is you can slide the x up under this one radical. So the next thing I'm going to do is that step right there. So I have the integral from 1 to 4. 2 pi is a constant. You could take it out of the integral right away. That's fine. But anything with x in it, you're going to have to leave behind. So this gives me x times the quantity 1 over 4x plus 1, integrated with respect to dx. So now we're going to have, and I'll go ahead and take the 2 pi out just to make it simpler. So we have 1 to 4. And if I were to multiply that out, and I were to reduce it, x times 1 over 4x is just going to give me 1/4. And x times 1 gives me x, and then I have dx. And then you may look at this and go, oh, hang on, that's just u substitution. Of course it is. So now we're going to do the u substitution part. So we have u equal to 1/4 plus x. And when we take the derivative, we get dx. And so it's already ready to go. Now, if we want to change our limits of integration, we can do that. We can say, but in this case, if we do that, they're going to become fractions and you may not want to go there. So you may want to just leave them as x values and go back. Totally up to you, whichever way you want to go. I'm going to go ahead and switch mine just because I feel like it. So when x equals 1, u equals 1/4 plus 1, which would be 5 over 4. And when x equals 4, u is going to be 1/4 plus 4, which would be 17/4. Right? So when I make the substitution then, I'm going to have that the surface area is equal to the integral now from 5 over 4 to 17 over 4 of 2 pi, which I forgot to take out, times the square root of u times du. Again, I didn't have anything else with my du because the derivative of 1/4 plus x is just 1. So I get the dx. Now I can go ahead and integrate this with respect to u. And when I integrate with respect to u, I get 2 pi. Remember, you can think of this as u to the 1/2 power. So you're going to raise it. It's going to become u to the 3/2 power. And then you want to multiply by the reciprocal of that. So this is going to be multiplied by 2/3. And now The next thing we need to do is evaluate between 5 over 4 and 17 over 4, or if you left them x values, you need to go back and substitute out u for 1/4 plus x. This gives me 4 pi over 3. And then I basically am going to have 17/4 to the 3/2 power minus 5/4 to the 3/2 power. And again, when you're doing it to the 3/2 power, it basically means you have 3 of these under a square root. So one is going to come out and then the others will be left behind. So when I simplify this, I end up with 4 pi over 3 times 17 over 4 times the square root of 17 over 4 minus 5 over 4 times the square root of 5 over 4. Now, I know that the square root of anything over 4 is going to pop out a 2, so I can simplify this a little bit more, and I can pull out the 1/4. So I have 4 pi over 3 times the 1/4 that was common to both, so the 4s will cancel, and I get pi over 3. And then I'm going to have 17 square roots of 17 over 2 minus 5 square roots of 5 over 2, with the 2 coming from the square root of 4 in the denominator. And then I can factor out the 1/2, and you'll see that I get for my final answer pi over 6, 17 to the 3/2 minus 5 to the 3/2, which is about 30.8 square units. Now, these are square units. These are not linear units. These are square units. So when we're looking at our graph up here, this area right here represents 1 square unit. So to paint this thing, I need to have over 30 of these shapes, that much wrapping paper or paint, all right, in order to get it completely wrapped up. Let's take a look now at example 8, which is the next example. When we're looking at example 8, we're looking to find the surface area of a solid produced by revolving x equal y squared about the y-axis instead of the x over the interval x from 0 to 9 and y from 0 to 3. Now, I had to be more specific here because saying x between 0 and 9 is not going to cut it, because when I look from 0 to 9, there are 2 sections here because it's a right opening parabola. And so I had to be specific, but I'm looking to revolve this section right here where y goes from 0 to 3. So I had to be more specific. Now we want to apply our formula. So let's go ahead and make note of everything we have and apply our formula. So we'll start with the arc length again. So we're going to find G prime first. Notice that this time we're going with respect to y because we're revolving around the y. So it makes more sense to do it that way, to write it as a function of y instead of a function of x. And in fact, that's the way it was represented, x equal y squared. So x is g of y. So now we've got, maybe I need to scroll up one more, find g prime of y, which is just going to be 2y. And then we need to square that. So g prime of y and square it, which is just going to give us 4y squared. And part 3, add 1, which is going to give us 4y squared plus 1. Now, looking at that right there, you should think, ooh, that looks like it might be possibly a trig substitution, because it just sort of has that feel, right? And in fact, I think that is what you can do to use this one. So we'll leave that to the integration step in just a minute. Now we multiply by the circumference, the average circumference of the frustum, which is 2 pi x. Now, x was given up here as y squared. So we're going to replace the x with y squared. So in our formula, we get that the surface area, now we have to integrate with respect to y. So from 0 to 3 of 2 pi, replace x with the formula y squared times the square root of 4y squared plus 1 with respect to y. Now, how are you going to integrate it? There are several options that you can pursue. It does look like I can do a trig substitution with tangent, set 2y equal to 1 tangent of theta, and solve it that way. It also is something that you could look up in a table. So go ahead and pause the video, work out the integral, and then turn the video back on, and we'll compare methods and see which way you went. So let's see which way you went. I know which way I eventually reverted to. It is a trig substitution. You make this substitution that 2y equals tangent of theta. So 4y squared plus 1, what's under the radical, becomes tangent squared of theta plus 1, which is secant squared of theta. So we replace this with secant squared of theta. Then since we switched the variable from y to theta, we have to replace the dy and the y squared. So I started with my substitution equation. I solved for y. When I squared it, I got tangent squared of theta over 4. So that replaces this y squared here. And then I took the derivative of both sides with respect to theta. And that gave me dy is 1/2 secant squared of theta d theta. And that replaces the differential. Again, when you have secant of theta squared under the radical, because of the way that we defined this particular operation for trig substitution, we're in quadrant 4 or 1, so we know that secant is going to be strictly positive. And so we can drop the absolute values around secant of theta, and we end up with pi over 4 tangent squared of theta secant cubed of theta d theta, which is a trig integral. Now, because this is odd and this is even, we convert the two tangent of thetas using the Pythagorean identity secant squared minus 1, which when we multiply that out, gives us this expression that you see here, secant to the 5th of theta minus secant cubed of theta. In the previous video, we did secant cubed of theta. So if you want to see how that's done, you can go there to see that. Secant to the 5th is very similar. It actually has secant cubed of theta as one of its steps. So you have to find this one in order to find this one. And you need integration by parts on both, where you're pulling off 2 of the secants at a time and using that for dv. And u becomes what's left. Now, I chose not to do all of that work for this particular video. So instead, I used a table of integrals. And I was able to show this becomes this integral right here, with the 2 pi being divided by 64. And we need to evaluate between 1 and 3, which gives you this expression you see here. Again, when you plug in the 0, this becomes square root of 1, but these become 0. So this zeroes out. Over here, this 2y term zeroes out, but this becomes the square root of 1, but the natural log of 1 is 0. So when y is 0, both terms drop out, and we just get the evaluation at the upper limit, y equals 3, which gives us 261 and a little bit of change square units. Now, there's one more example that I want to work for you. This is my favorite one to do when we talk about volume and surface of revolution, and that's Gabriel's horn. So let me take a look. I'll show you what the one that we just did looks like. So that's this one right here. So what we were able to find was the surface area of this thing. And you can tell it's sort of like an arena. It's a stadium that sort of goes down. It decreases as it goes towards the floor. And the floor actually touches the bottom on that side right there. And what we found was the surface area. Now what we want to do is we want to take a look at Gabriel's horn. Now, Gabriel's horn is very famous in mathematics circles because it has a really strange, startling, confusing, impossible result. And yet it is the result. It is real. And so we always like to work Gabriel's horn for our students because it represents sort of how weird things can happen when you go to infinity. Very, very weird things. So Gabriel's horn basically takes the graph of 1 over x from x equal 1 to infinity, and it revolves it around the x-axis. So we're taking a portion of that rational function and revolving it around the x-axis. So here's the graph of 1 over x that you see here. And then we start at x equal 1 and we go from 1 to infinity. And we're going to revolve this around the x-axis so that when you revolve it, you end up with something that looks like this. Now, this was taken from CalcPlot 3D. So I'll come over here and show you what it actually looks like on CalcPlot 3D. Now, you can't go to infinity over here. So what I did was I went far out and just sort of showed what it looks like. It looks like an old-fashioned trumpet, right? So you can see archangels or whatever blowing the horn. So it's an old-fashioned trumpet where the mouthpiece is over here, and this is the bell of the horn down at this end. So that's the shape that you get when you revolve that. And again, like I said, it does look sort of like an old-fashioned horn. So in this case, what I want you to do is I want you to find the volume first of Gabriel's horn, and keep in mind that it's an infinite region, right? We're revolving an infinite region. We're not stopping anywhere. We're going to infinity. We want to find out, will it hold a finite amount of stuff? Can I fill it with a finite amount of soda if I want to? And then after that, we're going to take and we're going to look at the surface area of it. And we're going to determine if we could paint it with a finite amount of paint. And this is where we're going to get our really startling result. So let's go ahead and get started. We're going to do the volume first, since the volume is simpler. Both of these are going to end up improper integrals because we're integrating from 1 to infinity. So we'll have to use our technique for improper integrals. So we're going to do the volume first. Remember that the formula for volume is going to be the integral from a to b of pi r squared dx, where r, of course, is given by the function, right? That's the radius. So when we look at our graph again up here, the radius, of course, is this little piece right here. That's the radius, and it gets revolved around the x-axis. So the radius is actually the function value 1 over x. So now we're going to replace this in here. We want to integrate from 1 to infinity of pi times 1 over x quantity squared dx. Now, in order to do this, it's an improper integral. So we take the limit as c approaches infinity of the integral from 1 to c. And I'm going to write the integrand as pi times x to the negative 2 dx. Now that's easy to integrate. You just use the power rule for integration. So this gives me the limit still. The limit is the last thing that we'll do. And this is going to give me pi x to the negative 1 divided by negative 1. And I want to evaluate this from 1 to c. I have to completely finish the integral first. Do not take the limit until you've plugged in the limits of integration. So I'm going to substitute those limits of integration in. And this is going to give me, well, I could simplify this a little bit. This is basically going to give me negative pi divided by x. So I've got negative pi divided by c minus a negative pi divided by 1, the lower limit of integration. So I've plugged in the two values there. Now that I have completed the integration by substituting the limits of integration, now I can take the limit. As c goes to infinity, a constant divided by c is going to go to 0. So this one goes to 0. And the second one, I have a double negative. So I get pi, and this is going to be cubic units. So in other words, I can fill it with pi cubic units of soda. It's an infinite space, but it's really, really narrow down there towards the mouthpiece. And it can be filled, completely filled with exactly that amount of liquid. Now we want to take a look at Gabriel's horn, and we want to look at surface area. So we've done the volume. And now we want to look at surface area. We know that we can fill it with a finite amount of volume. The question is, can we paint it with a finite amount of paint? So again, what we want to do is we want to apply our formula. We're revolving around the x-axis. So our surface area formula is going to be the integral from a to b of 2 pi, the radius, which is f of x, times the square root of 1 plus f prime of x quantity squared, the arc length formula with respect to x. You can also think of this as y. So 2 pi y arc length, or 2 pi r arc length. So our surface area is going to integrate from 1 to infinity, 2 pi. Our function is 1 over x. And now we need to take, I forgot to do that work first, so let's go to the side and do it. So I want to take f prime. When I find f prime, I've got 1 over x, so the derivative is negative 1 over x squared. And then I need to find that squared, which is basically going to give me a positive 1 over x to the 4th. So this is step 1, this is step 2, step 3, add 1. So I get 1 over x to the 4th plus 1. You could get a common denominator here. Whether you do or not is totally up to you. It just kind of depends on how you think or which point you want to apply the algebra steps. So now I've got 2 pi y, and I need my arc length. So my arc length is going to be, and I should go back to black, the square root of 1 over x to the 4th plus 1 integrated with respect to x. Now, this is an improper integral because of the infinity, so I'm going to have to deal with that. And I need to get all my x's into one location. So I'm going to take this 1 over x, and I'm going to slide it under into the radical. Now, 1 over x is not under the radical yet. So to get it under the radical, I first have to square it. Now, keep in mind that all my x values are strictly positive because I'm going from 1 to infinity. So taking the square root of something squared is not a problem here. So I'm going to move this under here by noting that the square root of 1 over x squared is equal to 1 over x for x in 1 to infinity. And that's including 1. So I can rewrite this now as the limit as c goes to infinity of the integral from 1 to c of 2 pi times the square root of 1 over x squared times 1 over x to the 4th plus 1, integrated with respect to x. Now I'm going to go ahead and do the distributive property and work that out. So this is going to give me the limit as c goes to infinity. The 2 pi is a constant, so I'm going to pull it out of the integral. I have 1 to c. And then under the radical, I get 1 over x to the 6th plus 1 over x squared integrated with respect to dx. Now, don't take out the 1 over x squared. You just get right back to where you started. What we want to do now is we do want to apply that algebra rule. Maybe you've already done it, and so yours is a little bit simpler now. We need to get a common denominator. We need to be able to split the radical up, but these are added, and you can't split radicals across terms. So we need to get factors, one thing divided by another. Now, 2 pi is a constant, and it doesn't depend on c. So in fact, I can pull the 2 pi out of the limit as well. And now I want to take the integral from 1 to c. I want to get a common denominator, which is x to the 6th. So I'm going to multiply this by x to the 4th over x to the 4th. And this will give me 1 plus x to the 4th, all divided by x to the 6th. And of course, if you reduce that, you get right back to where you started, so you know you've done it correctly. But now that I have this division, I'm able to split the radical, 1 for the numerator, 1 for the denominator. So when I split the radical, This is going to give me 2 pi times the limit. C is still going to infinity. Integral from 1 to c. I get the square root of 1 plus x to the 4th over the square root of x to the 6th dx. Now, normally when you take the square root of something, you need absolute values, but remember that our x's are all strictly positive. So we can drop the absolute value and rewrite the square root of x to the 6th as x to the 3rd. So I have 2 pi, limit tagging along, integral from 1 to c of the square root of 1 plus x to the 4th over x to the 3rd dx. Okay, now this is where students get stuck, and this requires something that you will learn in real analysis if you're a math major. It's a junior level course. It's quite a difficult course, but it's actually fascinating. It was one of my favorites that I ever took. It really forces you to understand the mathematics of what you're doing. This is not something that we can easily evaluate. Yes, you could go look it up in a table, but all I need to figure out is this finite or not? Is this a finite amount of paint? Now, if this +1 wasn't here, I could integrate it very, very easily. So the fact of the matter is, if we look down here, I know that 1 plus x to the 4th, and I'm erasing as I write again, has to be greater than x to the 4th for x in 1 to infinity, right? So as long as that's the case, I know that 1 plus x to the 4th is greater than x to the 4th. And that means the square root of this is greater than the square root of that. And so I'm going to, instead of evaluating this one, I'm going to evaluate one that's a little bit smaller, right? So this is going to be greater than 2 pi, the limit as c goes to infinity, of the integral from 1 to c of the square root of x to the 4th over x cubed dx. Now you may say, I would never think to do that. No, I wouldn't have either, but someone showed me and now I'm showing you. What we're going to find is that this blows up. It becomes infinity. In other words, this function, which is smaller than the one I resolved, Gabriel's horn, requires an infinite amount of paint. And then we can use the comparison test and say, well, if this requires an infinite amount of paint, this is bigger, it must also require an infinite amount of paint. So that's where we're headed. So now I'm going to go ahead and simplify that one right there. So this one becomes 2 pi limit as c goes to infinity. And again, we're going from 1 to c. The square root of x to the 4th is x squared. So this becomes x squared divided by x cubed. And when we reduce x squared over x cubed, we end up with 1 over x, which I'm going to write as x to the -1 dx. Now that one is one that I can easily evaluate. So when I'm looking at that particular one, or I can write it as 1 over x, whichever way you do. This is one that we know. This is 1 over u du, which is the natural log of the absolute value. So if you want to write it back in the 1 over x form to remind you of that, that's good. So this will give us 2 pi. Haven't done the limit because I haven't plugged in the limits of integration of the natural log of the absolute value of x evaluated between 1 and c. So now I'm going to go ahead and substitute those in. 2 pi, limit, c is going to infinity. And I'm going to have the natural log of c. C is strictly positive, right? Because it's to the right of 1. So it's going to infinity, but it's definitely a positive number. So I can drop the absolute values minus the natural log of 1. Well, the natural log of 1 is 0. So this gives me the natural log of c. Now, when you're thinking about this, you need to think about what the graph of natural log does as the value goes to infinity. So when you're thinking about the graph of natural log, and here's the graph of natural log, it goes up very slowly, but it does go to infinity. So as c moves to the right, the y value, natural log of c, goes to infinity. So this integral diverges and becomes infinity. So it does not exist. That means, believe it or not, that although we can fill Gabriel's horn with a finite amount of paint, or rather with a finite amount of soda, we cannot paint it with a finite amount of paint. I can fill it, it's finite, but I can't paint it. That region is infinite. Crazy, I know, but that's sort of where it is. I hope you've enjoyed this lecture on a surface area of a solid of revolution. In the next video, we'll be taking a look at work from a physics standpoint, and we'll also look at the work of springs a little bit, and then we'll get into the work required to pump liquid out of some kind of tank. I hope you'll join me for the next video.